Okay everyone, welcome back to Block 3. In this lesson, we're going to learn how the contour lines on a topographic map describe the shape of the land. This is one of the most important skills in land navigation because the ability to visualize the terrain on your map makes your experience through the wilderness more predictable and can help build your confidence before you ever step into the actual terrain. Before we get into the meat and potatoes, let's take a knee here and conduct a quick equipment check. For this block of instruction, you are going to need the 1 to 24,000 topographic map of Yosemite Valley. In the course description, I have attached a link to the USGS's online database where you can download a full digital copy of the map for free. But as an alternative to printing the entire map, I have also attached a small snapshot of the area that we will be focusing on. I still recommend that you download the full file so that you have access to the high-definition imagery, which you will be able to zoom into for close inspection. This will become handy for you to have when we start looking in detail at the contour lines. You will also need to download the Yosemite Legend, attached in the description as well. Alright, let's begin this lesson with a bit of vocabulary and explain the difference between elevation and altitude. Both are measurements of vertical distance. However, elevation refers to the height of a surface object above mean sea level, or MSL. While altitude refers to the height of an object above a surface, referred to as above ground level. Since we are learning land navigation and not air navigation, we will be referring to the elevation of surface objects and referencing it from the National Geodetic Vertical Datum of 1929, originally known as the Sea Level Datum of 1929. All of the elevations taken from our Yosemite map will be written as a number of feet above or below MSL. Keep in mind that depending on where they were printed, some maps may refer to elevation in meters. So let's start with our map's legend. Remember that the legend is where we can find information regarding contour lines, contour interval, and other useful topographic information. Topographic maps may contain several different types of contour lines. Take a look at the legend and find the section titled Contours. Notice that this map uses 3 types of contour lines: index, intermediate, and supplementary. Index contour lines are typically bold and are marked at intervals along their length with an elevation index, but you may need to trace the line a bit before finding it. Looking at the Yosemite map, you should notice that the index contour lines are found every 200 feet of elevation change. Intermediate contour lines are distributed between index lines, and the number of them depends on the contour interval. Remember that the contour interval is the amount of elevation change between 2 adjacent contour lines. On our Yosemite map, the contour interval can be found just below the bar scale and is noted to be 40 feet, which is why you will always find 4 intermediate lines between index lines. Supplementary contour lines are used to show subtle changes in elevation when intermediate lines are not enough. Adding supplementary lines between the intermediate lines provides for a more precise representation of slight elevation changes. Supplementary lines fall within the contour interval. They do not represent a full step change in the elevation. Rule of thumb is to split the contour interval for supplementary lines. They simply help to paint a more detailed picture of where subtle elevation changes occur between intermediate lines, or when the slope between 2 widely spaced intermediate lines is not uniformly distributed between them. Every contour line traces a path along the ground at a specific elevation. That means if you were to convert a single contour line into a route for you to walk, you could complete the entire loop without ever having to walk uphill or downhill. Some people trying to understand contour lines find it helpful when they see an image of a terraced mountain. Each terrace represents a specific elevation, and it follows the terrain exactly like contour lines. If you were to follow a single terrace around this mountain, your track's elevation would remain constant the entire way. Taken together, these lines create a three-dimensional picture of the terrain. But before we get into identifying land features, let's first learn how to use the contour lines to find the elevation of a given point. Remember that every contour line traces out a path through the landscape at a specific elevation. If we know the elevation of at least one of the lines on our map and the contour interval, we could theoretically find the elevation of the rest by just adding or subtracting the contour interval for each adjacent line. Thankfully for us though, there are index contour lines dispersed regularly across the map. In order to find the elevation of any point on our map, we only need to know what is uphill and what is downhill. If our point is downhill from an index line, we just need to subtract the contour interval for each line that we pass as we move from the index line towards the point. If it happens to be uphill, then it's just the opposite, and we would add the interval for each line that we pass. But what happens when our point doesn't fall exactly on a line? What if it falls between two? The generally accepted technique is to estimate the elevation between lines. When a point falls near the middle of two lines, simply split the contour interval and either add or subtract it as needed. If the contour lines are widely spaced, with no supplementary lines between them, such as they are here, then you can decide which line the point falls closer to and make your estimate accordingly. Since we're on the topic of point elevations, we should take a moment to discuss how to estimate the elevation of hilltops and depressions. As you look around the body of our Yosemite map, you will notice that many of the mountaintops have been officially surveyed and are marked on the map with an X and a number, such as this hilltop here. Many others, however, are not marked with an elevation. For these mountaintops or hilltops, you will have to estimate the elevation yourself from the map. Take a look here at this hilltop just to the left of the word ridge. To estimate the elevation here, you just need to find the elevation of the last contour line that encircles it, and then add to that half of the contour interval. In this case, the last contour line encircling the top is here. So let's find our closest index line and add the contour interval for each line as we head towards the peak. Here's the 8,000 feet index line. Our contour interval is 40 feet. So let's now head toward the peak, adding 40 feet for every intermediate line we pass along the way. This would be now 8,040 feet, 8,080 feet, 8,120. And here at this last intermediate line, we have 8,160 feet. Now we need to add just half of the interval to that, which gives us 8,180 feet. With this calculation, you can be certain that your estimate is no more than 20 feet off. There's only a single marked depression worth looking at on our entire Yosemite map, and it just so happens to fall on our excerpt sheet as well. Look down at the bottom right of your excerpt sheet in the area of Mirror Lake. At the bottom left of Mirror Lake, you will notice a triangle with a dot inside of it, with the letters B, M, and the number 4,094. Our legend tells us that the triangle with the dot stands for a horizontal control point with elevation. The number represents the elevation under the triangle. Now let's take a quick look at our legend and see how a depression is shown on our map. As you can see here, a depression is shown in the same way a hilltop is shown, except that the contour lines of a depression have tick marks that point inward towards the lower ground. You may find multiple contour lines within a depression, depending on how deep it is. If the drop in elevation is greater than the contour interval, in our case 40 feet, then an additional contour line with tick marks pointing downhill will be shown, as you can see here in this example. Take a look again now at our Mirror Lake benchmark. At the bottom left of the triangle, you will find the only depression worth mentioning on this map, and it's pretty weak. It is shown as a single contour line with tick marks pointing toward the depression. Since the closest index line is here, and although I cannot see the index on our excerpt, I can see that this index line is marked 4400. And if I just count the lines going downhill, I come to the next index line. Since I know there are 200 feet between index lines, I can subtract that from the 4400, which gives me 4200. Then the next index line here must be 4000. Now I just need to add the contour interval for each line I pass heading from this 4000 line to my depression. Here's one, so let's add 40 feet. That gives us 4040. Here's the next, that gives us 4080. And now we still need to move uphill to where the depression begins, so we add another 40 feet, which gives us now 4120 at the edge of the depression. Now, as I said earlier, we subtract half the contour interval from the last encircling line, so 4120 minus 20 gives us our estimated elevation of 4100 feet at the bottom of the depression. In this way, the contour lines are like a ruler laid out over the terrain that we can use to measure elevation anywhere on the body of our map. But contour lines also have a secret that they share with some people who take the time to pay attention. Don't forget that as we move horizontally across the contour lines, we are not only covering elevation change, we are covering distance as well. Think about that on your own for a moment while you look at the area between Indian Ridge and Basket Dome on your map. The secret lies partially in the relationship that contour lines have with horizontal distance. Once you understand this relationship, the lines across your map will reveal a part of their secret to you. Let's take a minute to demonstrate this idea. Take a piece of paper, and as we did in Block 2, make a ruler on the edge of your paper using the meters line of the bar scale. Use the far left of the scale so that you can graduate your ruler in 100-meter increments, out to a distance of about 1,000 meters. You won't need any more than that. Let's say we're standing here at this intersection of the North Dome Trail and the Yosemite Creek Trail. To our left, we see a small trail that leads up to the hilltop to our north, marked on the map with the elevation 7,463 feet. Place your paper ruler so that 0 is where we are standing, and make a tick mark on your ruler where the hilltop is. I get about 400 meters. Now let's count contour lines between us and the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I count 10 lines. So if we multiply by the contour interval of 40 feet, we get 400 feet, or 121 meters. That means that over the course of roughly 400 meters of walking distance, we will gain around 400 feet, or 121 meters of elevation. Now take that same ruler with the tick mark on it at 400 meters, and lay it here at the Tenaya Lake trailhead. Let's count the number of index lines we will cross between the trailhead and our 400-meter mark on our ruler. 1, 2, 3, 4, 5. I count 5 index lines, which means we can multiply that by the 200 feet between index lines and get 1,000 feet or 304 meters of elevation change after we have walked the same 400 meters. This is an enormous difference in slope, from 15 degrees in the first case to nearly 65 degrees in the latter. To give you some perspective, a normal set of stairs is around 35 degrees. This is one of the most important things that topographic maps share with us, that experienced hikers take into consideration every time. Knowing the slope of the terrain can help you to plan routes that are accommodating to everyone in your group. Not being aware of or ignoring this information can make the experience less enjoyable for some of your group, or, in extreme cases, place them at risk of injury or worse. As the distance between contour lines becomes less and less, the terrain in that area becomes steeper and steeper, until eventually they get so close together that they form a single line which represents a sheer cliff. As the distance between the lines becomes greater and greater, the terrain in that area becomes more and more flat, until eventually there are no more contour lines, which indicates no elevation change at all, or flat ground. Now let's pivot to another aspect of contour lines that will help uncover the rest of their secret, which is terrain feature identification. Terrain features each have unique contour signatures, and your ability to recognize these features will make it easier for you to visualize the actual terrain in your mind. Let's begin with the easiest terrain feature to spot, and that's the mountaintop or hilltop. These are easily identifiable by closed loops on your map. And as you pan across your Yosemite excerpt, you can find many, such as the Indian Rock Hilltop or the North Dome. These closed loops may be small, but can also be very big depending on how pointy or flat the top of the mountain is. Depressions are also depicted by a closed loop. But as we discussed earlier, they're differentiated from hilltops by tick marks that point inward towards lower ground. Two hilltops together with an area of lower elevation between them is known as a saddle, which you can see here. Saddles are often found along ridge lines, which are represented by U or V-shaped lines that point away from high ground. A spur is very similar to a ridge, in that the contour lines are U or V-shaped and point away from high ground. But the difference is that spurs typically do not connect two or more mountaintops like ridge lines do. They are normally found jutting off the sides of individual mountains and are oftentimes created by the eroding effects of creeks or streams on their flanks. These areas of the mountain that seem to be eroded in are known as draws. I remember that because of how the water is normally drawn into them as it runs down the mountain. In fact, in many cases, it is this flowing water that over time has cut these draws deeper and deeper into the mountain and leaves the spurs between them. Draws are denoted on a topographic map by U or V-shaped lines that point towards higher ground. Valleys are usually flat areas of ground found between mountains, and in many cases there's a river or a large stream that runs along its course as well. You can re-illustrate for yourself mountaintops, saddles, ridgelines, spurs, and draws anytime you need to by simply making a fist. Take a look at your fist. When you look straight down at your fist, you can quickly see that your knuckles form the mountaintops. And these four mountaintops form a ridgeline across the top of your fist. Down the side of your fist, you can easily see that between your fingers run the draws. And your fingers themselves are like the spurs. This is a great way for you to always have with you an illustration of the topographic features that you can find on a topographic map. Once you can read these patterns, your map becomes a three-dimensional terrain model in your mind. You can anticipate ridge lines and draws, steep climbs and descending slopes long before you find yourself in the middle of them. With practice, you will find yourself actually walking the route and experiencing the terrain before you ever step off. Terrain directly affects your ability to move through the wilderness. I made a point to mention in our measuring distance block that the shortest route between 2 points may not always be a straight line. For example, when you see ahead of time that the terrain of the shortest route may put you or a member of your group at risk of injury, it's much easier then, in that moment, to accept the added distance that a circumvention might mean. But once you're in the thick of it, and have been for hours, the smart decision to backtrack out and start over becomes very difficult to accept. Before you know it, your willingness to accept the added risk of a shorter route has you exhausted and running out of daylight, injured, lost, or worse. When time is a factor, distance and terrain must still be considered together. Taking them individually is a beginner's mistake. We will discuss more about the pros and cons of navigating through different terrain features in our route planning block, where we will get a chance to put together everything we have learned along the way. I urge you now to spend a little time with your Yosemite map that you downloaded. Zoom in and really investigate what's happening with some of those lines in some places. Then, before you close it up for the day, zoom out. Look at the map in its entirety and see if you can visualize the lay of the land. It's this kind of training that will help you to build the skills you will need to have the confidence when it matters. So by now, you should understand how to navigate a topographical map, how to measure accurate distances across it, and now you have unlocked the secret of the contour lines. But there's a part of the equation we have yet to tackle. Get ready to meet the compass. We'll see you in block 4.